pass compiler, but we would get, you know, like a composition of compilers, which is already nice. Yeah, so in practice, so the infinity is conceptual in the sense that during the first stage, you can spawn as many arbitrary levels as you want. At some point, you're kind of relying that you're going to reach a level which is the default semantic, and you can short circuit to hardware.
So, isn't that we assume that we're not going to use a level higher than certain really big concepts, or?
So you can at runtime arbitrarily use as many levels as you want. You don't know in advance, but you're going to dynamically deal with the levels as you get them.
Okay.
Okay, so then so then how do we actually do this for reflection? So the idea is to basically stage the outermost and let the other levels kind of be in this mode of polymorphically deciding are they receiving staging commands, or are they receiving actual concrete, so are they receiving like code, or are they receiving concrete things that they can do? And then that would sift through the other level as well. So maybe it would be easier with the code example, but it's kind of like, you can imagine doing this in a few ways. So you could try to do this statically where you stage the best level and then kind of do this kind of, each level is able to deal with, it knows how to generate code or to interpret depending on what it has. Or you can do it completely dynamically, which is what the VM thing does in this up-down language. So it's a multi-level number calculus with lift operator, dead insertion, sketch polymorphism, and it's kind of similar to online partial evaluation. And I think it might be insightful to see a few of the code snippets for that. So basically, this is kind of what the evaluator looks like, and just to also maybe show the scheme version, since you've seen so this is the interpreter for scheme, so it's not that different from what we've seen like yesterday with these tagged things that you might have in this low-level language, which has spot, var, lift, and all that. And the Scala version looks like this, so that might be interesting to see for the types as well. We just have an environment, an expression, and return a value. And in our language, we have literals that become constant values. We have variables that are looked up in the environment. We have consts that become tuples. We have lam that becomes closures, and things like this. So that's kind of the multi-stage evaluation we have for this. Now, what is interesting is in some of those eliminator cases, you kind of have the stage polymorphism by saying if you have constants, you just do the addition there. But if you have code, you're reflecting it as a plus node in your accumulated code snippet. So this particular way of doing things, like it's kind of similar to lightweight modular scheduling. It's based on the idea that you would have a place to accumulate the code that you're generating, maybe putting it in some normal form, and that's what this kind of reflect operation does.
So my mental model for this right now seems to be like we have a piece of code that transforms some code before interpreting it, but I'm thinking that it's not the right mental model because we should be thinking of this as a power interpreter. So what's the difference between this and something that's like, oh, I'm going to do transformations of code and then at the end I'll interpret it?
Yeah, so this is a good question. So this is just the base evaluator of if you want, of the virtual machine of this tower of interpreters. So we're really doing one level only with this multi-stage evaluator. And then we're going to put it in a polymorphic machine and that can do multiple levels. So here, yeah. So this is still kind of one level, not a tower. But basically, we are generating code as a side effect. And then here we have, so the lift operation. So this is related to the normalization by evaluation that you mentioned yesterday. So here we're kind of going from a value back to an expression in normal form. And so it's an NVE-like operator because we're going to normal forms, but we have to deal with closures and things. So first, if we have a constant, we turn it into a literal expression, whatever it's kind of like just the arbitrary tags for this. And then if we have a tuple, so a value that represents a const pair, we turn it back into a const expression. And the most interesting case is actually lambda. So it's kind of like basically reflecting a closure back into a lambda by using the evaluation on the body and kind of extended body and things like this. So this is where the effect of normalization by evaluation happens. And yeah, so then we can kind of have this API for let insertion to do the verify and reflect blocks. And that's how we get to the metacircular evaluator. So this is again one piece of the puzzle. It's one stage, but we can have whether we're lifting, whether we're evaluating, whether we're expression, and that's kind of it's not exactly schema and stuff, we kind of language here, but it's pretty similar. And so we're kind of having this evaluator that we can put together. So notice that we have the maybe lift, which makes it explicitly polymorphic in some aspects. Like here, when we have a number, we can lift it as code or keep it as a number, and things like that. And then, so this happens in a few places. And then for the class operation, this is where the polymorphism comes in. We don't actually say that we're lifting or not. It depends on what the underlying class does. In the same way as this happens in Scala and the lightweight model staging, or this happens because it's relying on the underlying class of the VM to be stage polymorph. And then when we look something up in the environment, we're actually relying on whatever is in the environment, if it's code or not, that's what we're returning. And so now we can kind of define this split interpretation, so that's calling it with like no lifting and just like the source and we get that. Or we can do double interpretation, triple interpretation. So we're kind of creating a mini tower here, like just dynamically. And then we can compile, so we get the code for factorial, but if we add, which looks something like this in our language, but if we add other levels, we also get, if we basically just compile the topmost of the tower, we still get just the code for factorial. We don't get any obfuscation because the other levels will have sifted through the commands dynamically. Yeah?
I didn't understand why compiling at the top makes it compiled at the bottom.
Yeah, so this is also like one thing to keep in mind is that this makes sense in this very homogeneous setting, but basically what happens is that you can think of it as staging the topmost interpreter, right? So here we're staging the topmost interpreter. And the command will sift through the other levels below. And if they're code, they're going to stay code. If they're not code, they're going to be evaluated away. So all the overhead of the level is evaluated mostly away. So it's not super magical, I would say. It's kind of hard to get it to work if you have a level that is doing a lot of non-standard stuff. You will see the effect of that. But it's really just the stage polymorphism is allowing the levels to think of whether get basically whether if you have code, you're going to hand it down in some sense. That's the idea.
So the third row, I would read that as we are evaluating an evaluator, and then that evaluator is going to evaluate the compiling evaluator, and that compiling evaluator.
Yeah, so if you read it like this, it sounds pretty clear. I think there's a little bit, yeah, exactly. So you're evaluating the evaluated evaluator, but if you added even more levels, so like, yeah, so you can do this as many times as you want if you don't get any issue, but you can get some of the reflective aspects. Okay. So in addition to this, this is where you can do, so we had this example of a one-pass compiler, which has that, and then you can imagine having a modified compiler that does a transformation, and you would have a modified code for this. So for example, you could have a CPS evaluator that will actually make the code become CPS, or you can have a trace evaluator that will add logging, or like, yeah, so this is the base, the things like this. And the reflection, we can also maybe briefly mention this, so you can kind of have this evaluated meta level operation that will basically kind of, yeah, this is a bit subtle, but basically you can reproduce these reflective operations because you still have the full tower dynamically. And so there's more in this paper, but that's what I wanted to tell you about the core of staging. And one other thing we did, for example, more recently, is trying to apply this to side channel attacks. So basically, if you have this snippet of code here, if you're not actually, and you maybe have a region of memory that is out of access, but you kind of, this is speculatively executed. So you're starting with something out of access, and then that is basically in the secret part of the memory, and you need a transient trace in the memory of that. And so how do you deal with this? Like how do you kind of detect those situations, especially since the program looks constant time and things like this? So we're applying collapsing towers technique to basically specialize a processor that has all the architectural details with respect to some program, and basically get in result a snippet that has verified like low-level information about the timing of the program in the front, and then you can use off-the-shelf tools like this to resolve that. So there's more about this. Okay, so maybe in the last 30 minutes, I want to also talk about SMT as a backend, and just start with one experiment we did, inspired by staging. So I think staging comes up again in multiple ways, like this idea that you can kind of use your first stage to generate code. So, so the program I want to show is it's basically a Python library for program synthesis and symbolic execution. And it has a way of combining constraint solving with LLMs. I wanted to kind of see how good were LLMs at reasoning at different levels of abstractions with SMT. It is using kind of multi-stage programming to generate the SMT constraints. And basically the goal is to solve programming puzzles, so find an input to a sad predicate and things like that. So let's dive in and see an example. So I don't know if these are the most current results, but I have some. So example, a predicate might be, this is a set function in Python, which would be like, count the number of zeros in a string S and you get 1,000, but count the number of 00 and you get, sorry, of 00 and you get 0. And basically, we would like represent it like this in our system. We would kind of wrap these in somehow just to be able to do that. And then the generated SMT code, so that is that is in the SMT lib format, would look something like this. So we define the function for counting, like that. And then we get some statement that is fairly similar to the original. So we just say counting the numbers of A is 1,000 and counting the numbers of O is 0. So it's fairly, so the mapping between Python and SMT is fairly doable. The only problem here is this reliance on functions makes it hard to do synthesis, because if you're always like just generating functions instead of like relations, then you can't really run these things backwards.
Is that asserting that there is, that it's non-negative?
Yeah, so these were just like side conditions for what components of like using the count procedure. Yeah.
You're saying here the whole library is generating that display code automatically from the Python?
Yes, and the way it works is that it's actually doing something like staging. So you start, so here we have a simple example. You start with the sat function saying x is greater than 5. You kind of do this symbolic execution, which is really kind of relying, like in Scala, on these overloaded operations. And whenever you hit a code fragment, you're kind of deciding to generate code instead of like evaluating right there. And then at the end, you get a lot of SMT constraints. Basically, as a side effect, you're generating all these SMT constraints. So at the end, you get a big list of such constraints, like those. You get basically those results, but with their dependencies of like it's using this function, so we also have to include this function in the code. And then once you have that, you can just generate a solution and return it. So, and the power of using SMT is really that you're kind of delegating all the constraint solving. I think the drawback is that, I mean, I've tried to do a few things to make it work with like relations. So for example, I think particularly for list operations and things like this, it's very hard to translate Python list straight to SMT. Like you need to do an encoding, and each encoding requires a lot of functions, and that kind of makes it difficult to run backwards and do synthesis. So here we're doing synthesis of values from like given a Python program that describes this set function that describes a constraint on what would a predicate on the value, we're synthesizing the values. So let's see what actually happened when we try it. We get a timeout for this 1,000 and 0. So it's not ideal. But then what we can do instead is kind of do a simpler problem. So say with 3 and 0 instead of 1,000 and 0. And now we get an actual result. And that's a hint that we can pass to an LLM. And I mean, many LLMs actually will do much better if you give them a hint on a smaller result than if you don't give them any hints. But I tried also those results on Opus, and it was doing pretty well regardless. But it was kind of an interesting point that at some point they were doing much better with that. So for example, these are older results, but like so. Okay, so actually in this example, Gemini doesn't do as well. It does as well extrapolated end to end. And so these results confirm that the trend is really that it's kind of like trying to use them for this example-based approach kind of makes a little bit of sense. If you try to use them by giving them SMT that code to reason about, then it's actually too hard, even though they're pretty good themselves at generating SMT code. So I'm still experimenting with these results. And just to discuss, so this was one experiment with with SMT solving, and kind of like the way I was thinking of it was basically if the SMT fails, you kind of fall back to some sort of LLM integration and try to do a few things. And I also wanted to do a more straightforward project that uses SMT, and I kind of relied on thinking about the traditional thing that people do when they go from Hoare logic to verification conditions to SMT. So that's the typical thing you can do. And the idea there is that you have a program with like preconditions and postconditions. So that's an example. So you have like a program like this, for example. So precondition, there's no precondition here. Program says it's basically computing the max, and then it's asserting that it got the max. So then that would generate this one verification condition based on that. And then you can pass it to SMT as a solver and get like, okay, this actually successfully verified. And if you did something wrong with your post condition, for example, so here you just said, okay, the post condition is that m is equal to x, then you would get a counterexample with, say, x is -1 and y is 0, because you're not having the other case. So in general, I find it useful to use SMT as a kind of way to delegate the constraint solving, but I do feel frustrated by the limitation of having to deal with functions and not relations. And I know there's horn clauses, like constraint horn clauses that can help, but I haven't found a way to compile it. So I think an interesting project would be to do a relational SMT of some sort. And just to dive in a little bit in this implementation, which is one file. So basically we have a syntax where we have just a small language of arithmetic expression, a slightly bigger language of Boolean expression, because that also, the language of Boolean expression is also the language in which we write the preconditions and the postconditions. And then we have a language of statements with like skip, assign, sec, if, try. So this is really like an INC language, like from the course you might have seen and things like that. And then you have a program that is a precondition, a statement, and a postcondition. And then in terms of the verifier, so you need to have some boilerplate on substitution, but the key idea is that we have this one class traverser that returns the weakest precondition and verification condition. So these are following the rules of like the whole logic rules that are here for the weakest preconditions, and these are based on this really beautiful theory of whole logic, which you might have seen, where we can kind of think of we have these rules that are kind of like type checking rules, in that they don't go deeply into the evaluation of a program, but they can tell you whether a program verifies or not, right? So for example, maybe the trickiest rule is for assignment. If you're trying to establish a post-condition P on this assignment, then it's enough to do a substitution before, and it's kind of tricky because you might wonder why it's not the other way around or something. And then like so for example, this would be a wrong assign if you just try to do this, and that's because of like A might contain X, so that might not actually work. Okay, and then sequencing is easy, and then if is basically kind of like making sure those conditions align, and then you align it here. then the tricky part comes with while loops. But before we get this, there's also the consequence rule, which basically allows you to like widen your thing. So if you have a post condition, a precondition that is implied by the one you're deriving, you can put it here, basically making your statements weaker in some sense. And so for while loop, there is a question of how do you come up with this key that is everywhere here. It's kind of like the invariant of the loop. And this is where the weakest precondition doesn't really give you a solution, and you can try to do predicate abstraction or other things, but this is where instead you do an explicit, you explicitly give the verification condition. So how does this play out in the code? We see that we have, in the while loop case, we're relying on the invariant that is given by the body, and then we just make sure that the verification condition are met for this invariant. And this code is propagating both the weakest precondition and the verification condition in the special case of while loops. And so they're fairly similar and used together. And yeah, so now once we have this, it's kind of a simple translation to SNT, and I think there would be nicer ways to do this, but here we're really basically just transforming this abstract syntax into S expression to give it to the SNT solver. And then we get those, we basically have a runner, and we kind of get the result out. So this is how we get these kinds of things here with like, in this case, we get a figure and we get the actual counter result. So the way I think of SNT is that basically these basic solvers that have these theories incorporated, and I have found them in the past useful to do in a few projects like this, where their use is a backend, where the idea of staging comes in to kind of make the backend. So here, there's no particular staging, it's more like a traditional passing back.
Sorry. I guess I'm curious. Sorry. In terms, how difficult is it to scale these up to, like, having worked on a compiler, they're often pretty big, right? And it's kind of amazing to me that you're able to get as much out of what seems like relatively little code.
Yeah.
As you are.
Yeah. So okay. So that this code is fairly straightforward. I really wanted to see show a very thin layer to SNT, just like getting started. In general, the LMS kind of code can get quite big. So with Jack from a while back, I didn't mention it actually, but we had done a SQL C compiler in 500 lines of code. And so it started with a plain query interpreter, a stage query interpreter, especially in data structures, and switching the backend to C and doing more optimization. And I think Tarek actually pushed it much further with his team in terms of building a competitive SQL engine using that kind of approach. So it does work. There were many projects with DSLs and things like this. I think I like the conceptual simplicity of it. So this is why I'm attracted to it, and I can kind of push ideas in this route. I think in practice, there are some barriers like also say in terms of error messages, the levels kind of obscure things, and so there are some hurdles that make it maybe not really used in industrial settings as much. Yeah.
Could you actually go into more detail about some of those hurdles that you think are some difficulties with this style of programming?
Yeah, so let me of shows some of the limitations I got, so let me see if I can find this. Okay, maybe that will do. It's probably not the biggest version. But, so you get code like this out of the process. Let me see which one is true. Yeah, so anyway, I think I'm getting lost in my files, but I think one thing that comes is that here we're really doing this like this like I think it's really hard if you're, so in this case what is different, for example, is that we're not just building a compiler, we're building an analyzer using staging. So what's really hard is to go back and figure out where exactly does the analysis break down and for what reason. So for example, we will generate code like this and we will say, oh, okay, there was a timing leak because the two runs of the program didn't return the same assertion, but then going to find the source of the problem is very hard. And I think in debugging I had the same issue that it's very hard to debug at the high level when your problem is at the low level. So that I would say is the really issue.
It's the problem with the strings of O's. I remember right, the challenge, the problem was to generate a string that has O's, none of them next to each other. And I'm curious, like, what was the size of that problem, like, in SMT language?
Yes, so it wasn't.